Hello everyone, and welcome to my channel. This is an educational channel. We like to take a look at some great theories of everything and do particularly deep dives and to show you what they can do, how they can benefit your life, how they can help you with your paradigm shifting and your awakening to 5D consciousness. Today is our 459th video on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson was an American engineer, lived in the 20th century around 1959. He proposed his two fundamental postulates, which was kind of the essence of all of his work up to that point of figuring out how the universe operated. And then he took those two postulates, just two sentences, and he elaborated that into a theoretical universe through a deductive process, like an if this, then that type of approach. I actually did about 15 videos on that a year or plus ago. If you'd like to check out, those are called the outline of the deductive development of the reciprocal system. That's like 165 different steps that he took. And so then he took his theoretical universe and compared it with that of the scientists, the legacy scientists, the experiments, the laboratory experiments that they the measurements they made and compiled in their tables. So for example, we're looking today at the book Basic Properties of Matter from Larson. And in that book, he arrives at equations for many of the basic properties of matter, such as the melting point and the specific heats and the compressibility. And then he compares his results with the results of the legacy scientists. Now, Larson's reciprocal system, the two postulates, it's also called the universe of motion. And Larson's first postulate is where all of the kind of provocative stuff is. This is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, now the second postulate is more just kind of formalities, even though it's a lot of Larson's followers have disagreed with it, including me, basic parts of it. But the main idea that he's just trying to get across is that math works, geometry works, logic works. We're going to use those things to drive our theoretical universe. But he says that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Okay, now back to the first postulate. A universe is made out of motion, not matter, not energy, or anything else. It is made out of motion. Motion is the relationship between space and time. Space and time and motion have come in 3 dimensions. Space and time and motion come in discrete units only. And this is about, that's about what he said. Now, when he's talking about motion, he's really referring to a more generalized kind of motion that he calls scalar motion. And a scalar motion is a motion that has a magnitude, but it has no specific direction. A way to visualize scalar motion is to take a balloon and put some dots on it with a magic marker. If you blow up the balloon, all the dots will be moving away from each other. And they'll be moving away from, every dot will be moving away from every other dot. And even the locations between the dots will be moving away from each other. Every point on that balloon will be moving away from every other point. So there is no specific direction. Every dot is moving in every direction. So that is what Larson calls an outward scalar motion. Now, if you suck in the balloon and contract it, then all of the dots will be moving toward each other. And in every direction, every dot will be moving toward every other dot. And that's an inward scalar motion. Larson refers to these as the outward motion as the progression, the inward motion as gravitation. Okay, now he defines motion as the relationship between space and time. Basically, motion is a fraction with space or time as the numerator, time or space as the denominator. The ready example is speed. The bike is going 12 miles per hour, 12 miles of space in 1 hour of time. Space over time is speed. Okay, so that is our fraction for space over time, speed. And that is a reciprocal relationship. If you double the speed, you can say the bike is going now 24 miles per hour. Or equivalently, you can say the bike is now going 12 miles per half hour. You can multiply the space by 2 or divide the time by 2. That is a reciprocal relationship. So Larson's, that works for speed. What Larson does is he extrapolates that and applies it to all forms of really scientific phenomena. He says that all of them are motions. So not only is speed a motion, but acceleration is a motion, matter is a motion, energy is a motion, pressure is a motion, power is a motion, electrical capacitance is a motion, electric charge is a motion, force is a motion, density is a motion. These are all forms of motion, and they all have relationships between space and time in a fraction. Like matter in Larson's system is time to the third power over space to the third power. Energy in Larson's system is simply time over space, or really the inverse of space over time, which is speed. So we have those two inverses, speed and energy, and so on and so forth. Now, motion comes in 3 dimensions. Space and time also come in 3 dimensions. You can see that, the 3-dimensionality of space in what Larson calls coordinate space. This is our everyday common sense viewpoint of space. X, Y, Z coordinates, up and down, up, down, left and right, forward and back. And this is in a still frame, a still background. So we move through space, space is still around us. And, but at the same time, we are progressing in time. Time is always getting later and later and later, but in no specific direction. So we sense this space to be vectorial. We can establish directions, unlike the scalar motion. We establish directions in space, in this 3-dimensional space that we're accustomed to viewing the universe from. But time is progressing in a scalar manner, like on the surface of an expanding balloon. And so now Larson extrapolates that again because of the reciprocal postulate between space and time, and says, well, there must be somewhere in the universe that there is 3 dimensions of time in a still frame with coordinates, x-like, y-like, and z-like coordinates. And where space is progressing, space is always getting farther and farther and farther apart, but in no particular direction, just like on the surface of an expanding balloon. So Larson refers to these as the spatial reference system, or the stationary spatial reference system, and this temporal reference system, the stationary temporal reference system. And neither one of these reference systems can really do the job, which you can see from 3 dimensions of motion. There's 3 dimensions of time, 3 dimensions of space, but also 3 dimensions of motion. And 3 dimensions of space is only enough to occupy 1 dimension of motion. X, Y, Z coordinates, if you have, a particle moving through space, you need 3 dimensions. You need all 3 of those dimensions to define that motion. The coordinates of that motion. And the same is true with time. You need 3 dimensions of time just to occupy 1 dimension of motion. So our 3 dimensions of motion do not fit in either the spatial or the temporal reference system. They are kind of insufficient reference systems. Now, with the discrete unit postulate, space, time, and motion all come in only discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. And if you don't have a full unit, then you don't have anything. And if you have exactly 1 unit of space in 1 unit of time, space over time being speed, then you have what Larson calls unit speed. So the unit of motion, or unit of speed, is 1 over 1 equals 1. 1 unit of space in 1 unit of time. The same would be true for all other forms of motion. If you have matter, then you have 1 unit of space to the 3rd power over 1 unit of time to the 3rd power, because matter is time to the 3rd power over space to the. I think I said the reverse there. 1 unit of time to the 3rd power over 1 unit of space to the 3rd power, because matter is time to the 3rd power over space to the 3rd power. So every one of our scientific phenomena has a unit. It comes in units, and those units are derived from space and time. And if you have 1 unit of space and 1 unit of time, you have 1 unit of speed. Larson calls that unit speed, and that is also known as the speed of light. So the speed of light, 1 unit of space per 1 unit of time, that is the speed of the progression. So the outward motion of that balloon, except you have to consider that that's in 3 dimensions, the outward motion of that balloon goes at the speed of light. And Larson refers to that as the progression of the natural reference system. So we have a spatial reference system that's stationary, a temporal reference system that's stationary, and then we have this moving reference system called the natural reference system that is moving outward at the speed of light in all directions from all locations at all times. Omnipresent and eternal. Okay, so this is the 0 point of Larson's universe. He calls it the null point, or the state of rest in the universe is to be moving outward at the speed of light in all directions. So, again, one of the, sticking points for people is that they are unable to imagine motion without anything moving. But that's what we have here, and that's what you have to accept a universe of motion, is that you have to recognize that motion comes before anything that would be moving. And the thing that would be moving would be motion itself, too. And so that, along with the background, the idea of space and time as the background that we're moving through. In Larson's system, space and time are the contents of the universe, not the container of the universe, but the very contents. Everything is made out of motion, which is made out of space and time. Okay, so we've got this outward motion of the progression in all directions at the speed of light in all times and all places. This is the 0 point. This means that half of the universe is actually moving faster than the speed of light, and half of the universe is moving slower than the speed of light. Larson refers to these as the cosmic sector and the material sector, respectively. Legacy science and common sense, our common sense perception really only perceives the material sector. And we perceive the spatial reference system. And that's, this gravitationally bound system that we're in. So we see 3 dimensions of space and clock time. And that is a phenomena of the material sector. In the cosmic sector, that's where the temporal system resides. 3 dimensions of time and clock space. And these 2 systems are reciprocals of each other, basically identical to each other in their general contours, except that you have to interchange the roles of space and time. When you cross that unit speed boundary, you have to interchange the roles of space and time. That same thing happens in the small regions of both the material sector and the cosmic sector, inside a unit of space, and in the material sector, and inside a unit of time in the cosmic sector, because the discrete unit postulate says you have to have a full unit of space and you have to have a full unit of time before you have those things. So if 2 particles or atoms are approaching each other and they get to be only 1 unit of space apart, which is approximately 2 millionths of an inch, then they cannot approach any closer than that, because there is no such thing as less than 1 unit of space. So what they do instead is they flip and they start moving in time instead. And so they move outward in time, which is the equivalent of inward in space. So we see it as inward in space, but it is really occurring as outward in time. Larson refers to this as the time region, and refers to the phenomena as moving in equivalent space. Now, when we look across that boundary, not only do the rules invert, and now the progression is moving inward in equivalent space as opposed to outward in space before, and gravitation is moving outward in equivalent space as opposed to inward in space in the material sector. But our view is distorted. Equivalent space we see as a second power entity, and we also have to reduce what we see by the interregional ratio. What we see is only, there's a great deal of what we see that's lost in the translation. Okay, and the same thing occurs in the cosmic sector, except with time instead of space. Now, to get these atoms that do approach each other close enough in time, or the cosmic atoms that approach each other in space, or I have that reversed, the material atoms that approach each other in space, or the cosmic atoms that approach each other in time, what we have to do with the progression of the natural reference system is the source of everything. That source is harnessed by first reversing the outward flow of the progression in 1 and then 2 and then 3 dimensions. And at that point, the outward motion becomes an inward motion, which is gravitation. Gravitation is really synonymous with atoms. Atoms gravitate in and of themselves. There are no forces involved. If the way that you get that you see forces is by abstracting and coming up with a static view of a moving system, of a universe of motion. If you take one of those dots on the contracting balloon and you arbitrarily say this dot is motionless, then all of the other dots will be moving toward that one dot. And it will appear as if there is a force field there, that there is a force of attraction between all of the dots and your dot that you've decided is the reference point. But that is not true. All of the dots are moving under their own influence, under their own auspices. And it only appears as if they're attracted to this one dot because you've decided arbitrarily to make that one dot motionless. So that force field is the result of assigning a reference point, not the result of the motion itself. There is no force field. The gravity is intrinsic to each one of the dots or the atoms. So every atom has a 3-number combination of first you vibrate the outward progression, and that's a photon. And then when that photon gets rotated back again in another dimension, then that is a particle. And then when you combine 2 particles, then you get 2 photons and 2 rotations. And so an atom is a combination of motions. It's one primary 2-dimensional rotation, one secondary 2-dimensional rotation, and they alternate, and then one 1-dimensional rotation in the opposite vectorial direction that is optional and can be positive or negative. So that is how Larson notates his atoms, and those are the numbers that he uses to derive his formula for the basic properties of matter. So with that background, let's try to read for 10 minutes or so on from his chapter 7, Temperature Relations. We're right in the middle of this chapter. I'll try to fill in the gaps, but there's probably going to be a lot of gaps. So just pick up breadcrumbs as we move along, and just do the best you can. That's all that you can really do. You'll be surprised at how this stuff adds up, though. It was noted in Chapter 4 that in compression, the lowest electropositive elements do not take the minimum 111 factors of their electronegative counterparts, but have a 4 in A equals 4. A is the first number of the 3-number set in all of the elements of this class investigated by Bridgman. So Larson is basically, he assigns these numbers for, the atoms for the periodic table, but then he assigns a similar set of numbers for the compression factors, and then a similar set of numbers for the heat factors or for the temperature factors. And they're similar, but not the same. They're derived from the original atomic numbers. Okay, but have a 4 in all of the elements in this class investigated by Bridgman, the original investigator of this field. The reason for this difference in behavior is not yet known, although it is no doubt connected with the all-positive nature of the rotational displacement of these elements, meaning that they do not have a negative C component. Those are electropositives. But it is even more pronounced in the thermal factors. Except for the alkali metals above sodium, which as noted above have thermal factors even lower than the compressibility factors. The lower electropositive elements not only maintain the 6-unit minimum 411 or equivalent, but raise the effective magnitudes of their thermal factors still farther by omitting the n=1 section of the specific heat curve. That's like the rotation number. And so by omitting, the specific heat is the basically heat efficiency, the amount of heat that you have to add to something to raise it by a certain temperature, and the specific heat curves are segmented. There's a bunch of line segments with transition places of transition for each element. That's an important, probably the most important thing about both heat and compression here, is that the temperature is on an atom by atom basis, or at least a molecule by molecule basis. Every thermal group, a molecule, has its own temperature, and every variety of molecule has its own curve, specific heat curve, about how fast it heats up, how much heat you have to put in to get it to heat up a certain amount. And it makes transitions based on a couple different factors: the structure of the atomic bonding, and the geometrical bonding, and then also on the number of rotations that are involved. And when you move from section n=1 to n=2 of the curve, the specific heat goes down by a factor of 8, which is a factor of 2 to the 3rd power, because there's 3 dimensions of everything. So, and then, if it goes to n=3, then it is a factor of 27, or 3 to the 3rd power, from that original n=1. And so if it skips the n=2, right to the n=2 part of the curve, which increases the temperature scale by a factor of 8. This pattern is followed by boron and carbon, and in part by beryllium. The corresponding numbers of the next higher group, magnesium, aluminum, and silicon, also have n=2 from the start of the thermal motion, but here the second unit is one-dimensional rather than three-dimensional, which I'm not sure what he's talking about there. Beryllium combines the two patterns. It has the same thermal factors as lithium, but a dimensional multiplier halfway between those of lithium and boron, the two adjoining elements. The option of one dimension or 3 dimensions, well, here he's going to explain what I didn't get here. The option of 1 dimension or 3 dimensions is open whenever motion advances from 1 unit to 2 units, but not under any other conditions. One would think that that sounds a little bit like an ad hoc assumption, but we'll give him the benefit of the doubt for now, and maybe he'll explain this. 3-dimensional motion of one displacement unit is meaningless, as 1 to the 3rd power equals 1. After 2 units, there is no motion, as there cannot be more than 2 units in linear succession, for reasons that were discussed in Volume 1. But 2-unit motion can be either 1-dimensional or 3-dimensional. At the point where the advance from 1 to 2 units takes place, the motion is therefore able to take the dimensions that are best suited to the existing situation. A 1-dimensional increase in the value of n results in increasing the temperature scale by a factor of 2 rather than 8. The alkali metals, which diverge from the normal electropositive behavior in a number of respects because of their low electric displacement, follow the same pattern as the elements listed in the preceding paragraph, but 1 step lower, as indicated in the following comparison. And so now he's just comparing these alkali metals with other electropositives. As we found in the specific heat investigation, the electronegative elements below displacement 7 have a half size initial negative specific heat level. Sorry. 1/9 unit instead of the normal 2/9. And those initial specific heat level come from the photon or photons that are at the core of the atoms. 1/9 for each. So I'm not sure why these half-size ones would apply to atoms, but he may explain that. Actually, I think I am going to just stop it right here because this paragraph goes on forever. And I will also say, I think I stated that wrong, that when the specific heat curve goes from n equals 1 to n equals 2, that means that the temperature scale goes up by a factor of 8, not down. Because this is all statistical, which is part of Larson's second postulate. He's using statistics in order to be able to derive through deductive reasoning his theoretical universe. And statistically, an atom is going to stay at its lowest energy configuration, which is the solid state. And so the machinations of these atoms shifting from n equals 1 to n equals 2 and then to n equals 3 is to make it so that you can put more temperature into the system without it causing the atom to go out of the solid state and into the liquid state, which is less probable. The solid state is more probable than the liquid state. So the atom is going to do everything that it possibly can do to avoid getting to the melting point. And so when it increases its specific heat number, it increases the amount of heat that it can handle without moving anywhere, without moving much closer to the melting point line. So that's where you get these steep curves. At first, you don't have to add very much heat at all to advance it. Like, say if the melting point is over here, you don't have to add too much heat at all to get it to go here. But then once it goes to n equals 2, then the slope goes like this. So that's just clarifying that. We'll come back tomorrow and talk about more heat. Thanks for tuning in.